Okay, so we're going to go ahead and get those clicker questions done that for 3/20, so last Friday. And I believe the first one here, yes. First one we're going to start with is some examples of using Lenz's law. So the first one was a north pole of a magnet is moving towards a copper loop as shown below. So north end of a magnet is above and it's moving towards a copper loop which is below it, and the north end of the magnet is down. So if you're looking at the loop from above the magnet, would you see a induced current that goes clockwise or counterclockwise? So let's think through this problem. There's a couple steps here. First, we have to recognize, so we know when we talk about induced current, you immediately have to think of, is the number of field lines increasing or decreasing? So let's look at this problem. Let's actually see what field lines are there. Well, we have a magnet, and this is where you have to remember that a magnet, it's a little hard to fit in here, but makes a magnetic field. It ideally it'd be more of an oval, but unfortunately that kind of overlaps with this. But it does something like this, and then it kind of comes back into here. So it comes out of the north end, wraps around, and it goes into the south end. So you get a bunch of magnetic fields that are going down. So you get magnetic fields going down due to the north end of the magnet. Draw this a little bit out of the way of that velocity. Okay. So if we're moving it down, as we get closer with our magnet, that means we are increasing. So flux, so number of field lines going down is increasing, because as I get closer, the field strength gets bigger and bigger and bigger. Field strength going down specifically. This loop does not want more going down, because that's what Lenz's law says, and Faraday's law. And so it's going to generate one in opposite direction. So if I'm getting more down, I don't want more down, so I make some up. So I point my thumb up, and you see your fingers are going to curl, if you looked at it from the top, are going to curl this way, which if you're looking at this from the top would be counterclockwise. So you get a current that goes counterclockwise to oppose the increasing lines going down. Okay. The next one. This one, I have a north end of a magnet pointed towards a loop. The magnet is no longer moving, but my loop is just spinning in place. And it's not it's just rotating like a hula hoop. So it is not doing this. Nope, not doing that. It is rotating in that plane such that this plane is always makes an area vector that's parallel to the magnetic field from this magnet. All this to say, the question is the induced current clockwise, counterclockwise, or equal to 0? And in this case, we look at it, do we get more or less field lines as time goes on? And the answer is, we don't get any more, we don't get any less. Because, and an easy way to kind of check this, imagine this thing rotated. If you closed your eyes, you saw it, you closed your eyes, someone rotated it, and you open your eyes, you wouldn't tell that a difference had even happened. No matter how much they rotated, no matter how little, no matter how much, nothing changed as far as you could tell. So if nothing changes as far as you can tell, our flux hasn't changed. We haven't increased the area, we haven't increased the field strength, and we haven't changed the angle with respect to it. So those three things haven't changed, you get no flux. Okay. The next one, we have our 3 charges of the review question. So this is not going to be about flux. So the question is, what is the direction of the electric field at point P given the charges below? And note that the charges all have equal magnitude. So I have a positive charge at the top. It's an equilateral triangle with a positive charge at the top, a positive charge in the bottom left, and a negative charge in the bottom right. So remember, to find electric field, we do one charge at a time. So let's look at this top charge. We do one charge at a time, and remember that positive charges make electric fields away from them, and negative charges make electric fields towards them. That is the rule. So we need to remember that we're going to do one charge at a time, and just remember that they point away or towards. And they're stronger or weaker depending on distance. All of these distances are all the same, so that's going to make our life easier. So we get the top one, makes an electric field down. I'm going to just number these. This is charge 1, this is charge 2, this is charge 3. So we get one straight down. The positive one makes one up and to the right. And the negative one makes one down and to the right. Okay, so now how do we get the total direction from these? Well, the way I did this, so you can, for one, literally take these arrows, and you can always do tip to tail. So I'm just moving them over here to make my life easier. So there's one. The net vector is down and to the right. So you could just draw it for one. The other way is you could recognize that this one, due to symmetry, is going the same amount up as this one's going down. So the y components will actually cancel, but the x components will add. And so you'll get one that's longer and to the right, and that one's going to add with the one going down to give you one that is more going to the right than down. Okay, so pretty quick, we're moving through these. I think we just have 2 more quick ones. This one was the moving rod, and we asked what was the flux through the current loop. So this is very quick. Flux, the equation for that, if you ever see magnetic flux, immediately go to the equation for magnetic flux. B times A times cosine of theta, where theta is the angle between the area vector and the magnetic field. In this case, theta is 0. So you just get B times A equals B times X times L, where X is the width of it and L is the height, because we want the area inside of this thing. And so you just plug in those values. You plug in 3 e to the minus 6 times 2 times 3. 3 times 2 is 6. 6 times 3 is 18. So you get an extra, don't even need to use a calculator for that one. You get an extra order of magnitude. Okay. And the last problem was just figuring out that same problem, direction of current, if the rod's moving to the left. So we use our Lenz's law if we're ever trying to find direction of induced current. We can say the rod's moving to the left. Again, you can imagine what I like to do with these. That kind of makes it easy. This is what I kind of visualize in my head. I imagine it at a later point. And you see here at this later point, I've lost magnetic field lines going into it. So this current needs to make more going into it. I've lost them going into it, so I need to make more going into it. So I point my thumb into the page, and my fingers curl clockwise. And that's it. All right, so there's all the solutions to the clicker questions. Got through these much quicker than last time. If you have any further questions about these, please either email me or come to my office hours, and I'd be happy to answer them. All right, have a great day.